friends, in the video NCERT Chapter 1 Real Numbers Class 10. We shall be studying this chapter under 5 main topics: Euclid's division lemma, Euclid's division algorithm, the fundamental theorem of arithmetic, irrational numbers, and finally rational numbers and their decimal expansion. Wherever necessary, we shall also discuss some theorems as well. But before all this, let us recall what real number is. Suppose if we take all the rational numbers and all the irrational numbers and put them inside the bag will be full of real numbers, which means real numbers consist of rational numbers and irrational numbers. We already know that numbers that can be written in the form p by q, where p and q are co-prime, that is, they don't have any common factor other than 1 and q is not equal to 0, are said to be rational numbers, while its reverse, that is, numbers which cannot be expressed as p by q, are called irrational numbers. Before we start our first topic, that is Euclid's division lemma, and the other, Euclid's division algorithm, it is important for you to understand what does an algorithm and a lemma mean. Algorithm is the step-by-step method to solve a specific problem, or an algorithm is a series of well-defined steps which gives procedure for solving a type of problem. And in this case, Euclid's division algorithm is used to find HCF, and lemma is a proven statement which is used to prove other statements like formulas. But in formulas we have numerical values, while lemma is a statement. Let us see what does Euclid's division lemma state. It states that if we have two positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where r is greater than or equal to 0 but less than b. Now let us move on to Euclid's division algorithm. It is based on the Euclid's division lemma, and so they are closely interlinked. And it says that any positive integer a can be divided by other positive integer b in such a way that it leaves a remainder r that is smaller than b. Now let us see how this algorithm can use to find the HCF of two positive integers, say a and b, with a being greater than b. Step 1. Apply Euclid's division lemma to a and b. So we find whole numbers q and r such that a equals to bq plus r. If r is equal to 0, that is, the remainder comes 0, then b is the HCF of ab. But if r is not equal to 0, then apply the division lemma to b and r. Continue this process till the remainder is 0. The divisor at this stage will be the required HCF. Now let us study about the fundamental theorem of arithmetic. We already know that every composite number can be expressed as the products of primes in a unique way. For example, 210 is equal to 2 into 3 into 5 into 7, or 3 into 5 into 7 into 2. Here the only thing changing is the order in which they occur, but the numbers, the primes, are the same. So the fundamental theorem of arithmetic states that every composite number can be expressed or factorized as product of primes, and this factorization is unique apart from the order in which the prime factors occur. Now let us see how it works by taking an example. Consider the numbers 4 raised to the power n, where n is a natural number. Let us check if there is any value of n for which 4 to the power n ends with the digit 0. We know that if any number ends with the digit 0, it would be divisible by 5. Therefore, if the numbers 4 to the power n for any n were to end with the digit 0, then it would be divisible by 5. That is, the prime factorization of 4n would contain the prime 5. This is not possible because 4 raised to the power n is equal to 2 raised to the power 2n. So the only prime in the factorization of 4 to the power n is 2. The uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 4n. So if 5 is not there in the prime factorization of 4 raised to the power n, it could not end with the digit 0 for any value of n. Now let us study about irrational numbers. We have already studied that the numbers which cannot be expressed in the form p by q are called irrational numbers, and examples of irrational numbers are root 2, root 3, root 5, or in general say root p is an irrational number if p is a prime. Till now we have already studied two of the theorems of this chapter, that is Euclid's division lemma and the fundamental theorem of arithmetic. Now let us see the third theorem of the chapter. It states that if p is a prime number and it divides a square, then p also divides a, where a is a positive integer. For example, if 3 divides 81, that is 9 square, then 3 divides 9. Or if 5 divides 625, that is 25 square, then 5 divides 25 also. Let us now prove our next theorem, which is root 2 is irrational. We shall be proving this by method of contradiction. Let us assume to the contrary that root 2 is rational. Then root 2 will be equal to a by b, where a and b are co-prime and b is not equal to 0. So b root 2 equals to a. If we square both sides, we will get 2b square equals to a square, or b square equals to a square by 2. Therefore 2 divides a square. Since 2 is a prime number, therefore from the theorem 1.3, it follows that 2 divides a as well. So we can write a equals to 2c for some integer c. Therefore, substituting for a in equation 1, we get b square equals to 4c square by 2. That is, b square equals to 2c square, or b square by 2 equals to c square. This means that 2 divides p square and so 2 divides p. Again using the same theorem 1.3 with p equals to 2. Therefore, a and b have at least 2 as a common factor, but this contradicts the fact that a and b are co-prime and does not have any other factors in common other than 1. This simply means that our initial assumption was wrong, which has led to this contradiction. So we conclude that root 2 is an irrational number. Now try to prove root p as an irrational number where p is a prime. Let's now move on to rational numbers. We shall see some theorems in this section. Theorem 5th of this chapter. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime and the prime factorization of q is of the form 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. For example, 0.375, which is equal to 375 upon 1000, or 375 by 10 cube, that is 3 into 5 cube upon 2 cube into 5 cube, or 3 upon 2 cube. Let us take one more example. 0.0875, which is equal to 875 upon 10,000. 875 upon 10 to the power 4, which is equal to 7 into 5 cube upon 2 to the power 4, which will give 7 upon 2 cube into 5. Again here, 0.0875 is a rational number with a terminating decimal expansion. We have written it in the form p by q, and q, that is the denominator, is in the form 2 to the power n into 5 to the power m. Let us see the next theorem, the 6th theorem, which is the reverse of 5th theorem. Let x equals to p by q be a rational number such that the prime factorization of q is of the form 2 to the power n into 5 to the power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. Let's take an example, say 3 upon 8, which is equal to 3 upon 2 cube. We can multiply 5 cube with both the numerator and denominator and we will get 375 upon 10 cube, which is equal to 375 upon 1000, or 0.375. See, 3 upon 8 is a rational number where the denominator q, here in this case 8, is of the form 2 to the power n 5 to the power m, that is 2 cube into 5 to the power 0, which is equal to 1 actually. And finally we see that its decimal expansion terminates. Now let's see what happens if the denominator is not of the form 2 raised to the power n into 5 raised to the power m. That is the theorem 1.7. Let x equals to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to the power n 5 raised to the power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating and repeating. For example, if you divide 1 by 7, you will get 0.1428571. Here you can see that the numbers are repeating after a certain point of time. Therefore, 1 upon 7 has a decimal expansion which is non-terminating repeating. This was the last theorem, and by this we have completed our chapter Real Numbers. And if you have any doubt in this video or in the chapter, let me know in the comment section below. And if you have not subscribed my channel yet, please subscribe it and stay tuned for more videos.